Hi, everyone. Thank you for joining us today. So we looked at aqueous film forming foam impact on per and polyfluoroalkyl substances on soil contamination, and this was a case study of select U.S. military bases. So PFAS has been an emerging contaminant, and it's been gaining traction in the public eye due to recent studies of its health impacts, how it bioaccumulates, it doesn't break down, so it definitely grabbed our attention. PFAS is a group of highly durable molecules whose key characteristic is that they typically have carbon chains surrounded by fluorides. With these group of chemicals having unique properties that are now being found in high levels in groundwater, we wanted to take a look at how they move in soil so we could have a better idea of the possible interactions between specific PFAS that were occurring, and because by a better understanding of how they move through soil, remediation could be more specifically targeted. A literature review found that the overall PFAS trends tend to have higher levels in the soil concentrations in the soil profiles, as if the soil is acting as a type of reservoir. Taking this into consideration, we looked at AFFF foam because it is one of the highest sources of PFAS contamination, and it's applied directly to the ground. So even though we were limited in that we were investigating movement potentially years after the military base had stopped using it or changed its formula of the foam, because it was typically used from 1970 to 2001, it didn't involve any other types of transport because PFAS being very soluble in water, it could be transported through air, water, or soil. So we thought this was the best contamination source to investigate what we were trying to find. We selected bases in random parts of the country so we could have different soil profiles to compare, but we were limited in that we could only use ones that had boring logs available from the DoD reports and contamination measurements through both the DoD and the SSEHRI. But we were able to pick two. Case site 1 was in Louisville, Tennessee, and case site 2 was in Phoenix, Arizona. So two separate parts of the country. And through USDA soil surveys, we were able to confirm that they were very different soil types, and they had enough data that we could analyze thoroughly. So figure 1 shows total PFAS concentrations over depth of 3 close locations in both case sites 1 and 2 that we examined. Because we could not account for how much each Air Force base used over those years, we graphed the concentrations on 2 separate axes. So we could still compare the trends of the slopes, and we could see case site 2 has a much steeper drop in concentration per depth, whereas case site 1 shows longer retention rates. So we wanted to investigate what could be the cause of this difference. So we were able to use the boring logs provided, and in figure 2, where case site 1's boring logs was collected, and figure 3 shows where case site 2's boring logs were collected, we were able to make a graphical adaptation of the boring logs and the different PFAS analytes as they changed to the soil profile to get a better understanding of which specific PFAS may have been following the trends or may not have, and what may have influenced the transport rates. So figure 4 over here shows the breakdown of case sites and how the analytes changed. And we can see case site 1 is dominated by clay content, and it shifts from high clay content to a more silty clay. And we see the general trend of most analytes decreasing with depth. However, we see an exception with PFOA and PFHPA. Figure 5 shows the same breakdown for 3 boring logs from case site 2, which was a well-graded, loose, gravelly soil, which would explain the much higher transport of contaminants we saw compared to case site 1, because gravelly soil would have a much higher permeability than clay soil. Figure 5 also shows how, for the most part, the analytes follow the trend of decreasing with depth. However, PFOA concentrations in the second bore log increases with depth, like in case site 1. And the third bore log at the bottom, we see PFHPA. While it did decrease, it still remained at a detectable concentration 16 feet and around the same amount detected as around the first foot. Overall, we found that the PFAS contamination in the soil did match the trends from the literature in seeing a decrease in depth, indicating soil is acting as a type of reservoir for this type of contamination. However, when we looked at specific PFAS molecules, we found that not all of them followed this trend, and we've listed some possible explanations, one of which there may have been an interaction going on between the functional groups because figure 6 shows how the molecules PFOA and PFHPA are both long-chain PFCAs, a group of PFAS that contain carboxylic acids. When looking at the molecules that were retained at higher levels of the soil, we found permeability and texture of the soil definitely played a role in the amount retained. And a factor that could also explain the higher retention rates is cation exchange capacity in the clays interacting with the PFAS functional groups. Because figure 4 shows a much higher retention rate of PFSAs, these are PFAS group that contain sulfonic acids as seen in figure 6. So this is what we basically found. And the case study was fascinating in that it supported previously found general trends, but the individual PFAS molecules were observed to be behaving inconsistently with this trend. This project really highlights the need for more studies of individual PFAS molecules transport through soils, preferably in a more controlled environment. And in the future, I really hope to do that. So thank you for listening. I've been Gabrielle Goldner, your host today, and I hope you can join us April 15th from 2 to 3 p.m. if you have any questions or you want to discuss anything.